Hi grade 12s, unfortunately I'm not going to be in school on Friday, so I've made a video for you to go with this. As you can see, this is 2 lessons worth of content here, and what I would quite like to do is for you to take this lesson on Friday and Friday's homework to work through the notes for this, which is quite long, but then we will save doing all the homework for next lesson. And in fact, we're going to cut this out until after the October break. So just to repeat, we're going to go for trying to work through all the notes as today's work and homework, and then in our first class next week we will spend some time looking at the homework and having a chance to ask any questions from the last couple of lessons. So the first thing I'd like you to do is to pause the video and have a go at the starter questions on page 27. Alright, hopefully you've had a go at these now. If you're confident, obviously skip through and just check the answers. If not, I will go through this as well, because I think it introduces this whole idea quite well. So last lesson we were looking at equations of lines using vectors. Today we're going to be looking at motion, but there's going to be some crossover between the two. So we're starting with this. Consider a boat which is initially at the point A with coordinates 5, 1, which is moving with a velocity of -2I plus j kilometers per hour. And just conventionally, I is the unit vector east and j is north, and this is measured from a port which is at the origin. Okay, so we can see from the arrow which way the boat is travelling, and from the question we can see that in 1 hour it moves 2I and 1j, that is its position. 1 hour later, 2 hours later, 3 hours later, and so on. Okay, so either from just looking at the graph or by thinking about the position, we should be able to write down the position vector after 1 hour. It's this point 3, 2. And then after 2 hours, it's 1, 3. So in general, what's happening, we're trying to write down a position vector after t hours. So this is where it starts to look a little bit like the vector equation of a line. To find where it is after 10 hours, for example, I'll be starting with that coordinate A, which is 5, 1, and I'll be adding 10 lots of what it does each hour. So it's doing -2, 1 each hour, and I'd want 10 lots of that. So obviously, if I want to see how long it is after t hours, I want t lots of that. So that's an expression for the position vector of the boat after t hours. And you can see the similarities with what we were doing yesterday. We have a position vector at the beginning, which is the starting point of the boat. And we have a direction vector multiplied by time. And the direction vector is actually the velocity of the boat. So this we were thinking about as a position vector. It's the initial position. And the other vector we were talking about as a direction vector, it is the velocity, which of course is how its position is changing, so it is the direction vector. So I'm going to write here that this was our position vector, and this is our direction vector. This is really key to what is going on, understanding that we have this initial position, but the part of it that tells us how the object is moving is from the direction vector, just as we had yesterday. Okay, what can be said about the x-coordinates of the displacement vector for the boat when it is directly north of 0? Okay, so when it's directly north of the port, we are on the y-axis, and of course the x-coordinate equals 0. So if we know that, well, we can take our answer to 1c, the position vector of the boat. We can say, if I want to find out when it's directly north of that, I'm going to take the x parts, 5 plus t times -2. I'm going to write that's 5 minus 2t. And we're saying that that displacement needs to be 0. So of course that lets us solve for time now. Time is going to be 2.5 hours. Okay, so in 2.5 hours, the boat will be in a position that's directly north of the port. A slightly trickier question. Of course, we can't see when it's directly east or west of the port because it's starting at A. So we can't extend this line back the other way unless we're told that it had been travelling this way for some time. And obviously we're not going to be able to see when it's south of the port. It's not going to reach that point. But this is an interesting question. What can be said about the x and y coordinates of the displacement vector when the boat is northwest of O? That is on a bearing of 315 degrees. So if it's northwest, it's going to be over here somewhere, isn't it? Like where this intersects with the direction vector. And if we think about that, that is the line y equals negative x. And we know that the x and y coordinates, well, the y coordinate will be the negative version of the x coordinate. So what we can say is that the y coordinate is equal to the negative version of the x coordinates. So once again, we can take that, we can go to our answer to 1c, the position vector, and we can say, well, the y coordinate is 1 plus 1t, and we want to find out when is it equal to the negative version of the x coordinate. Okay, once again, we've got a simple linear equation to solve to find time. So I'm going to make this 6, I'm going to make that t, so t is 6 hours. Having a look at this, yeah, it looks sensible. I mean, it's got to here at t equals 3, so I could imagine it being at a position northwest of the port at t equals 6. And of course we could say, well, what about when it's northeast? So somewhere along this line, well, the x and the y coordinates have to be the same. And the same with southwest and southeast, which this boat is not going to reach. But it gives us some ways of thinking about the relative positions of the x and the y components of that. Okay, so these are some key points. The velocity of an object is a vector quantity. It needs both a magnitude and a direction to define it. So a velocity of 10 meters per second north is a different velocity to 10 meters per second east. They're the same speed but in different directions. Velocity represents the change in displacement of an object during 1 unit of time. An object's speed is a measure of the distance covered in 1 unit of time. So speed is the magnitude of the velocity vector. And we can use this symbol, this absolute value symbol around the velocity to stand for the magnitude. And we know from the formula guide and what we've done before that we use Pythagoras' theorem to find that value. So if we have a velocity value, we can calculate the speed the object's travelling. The position of a particle moving with velocity v and whose displacement at time 0 is r0 can be given by this equation. So the position is its initial position plus the velocity times time. And obviously that looks very similar to the equation of a straight line in vector form. So let's look at an example of this. A ship A has position vector 3i plus 4j at 1 o'clock, where I and j are east and north of a harbour. 2 hours later, its position is 2i plus 8j. So we find out that where it's moved to 2 hours later. So if we want to find the velocity, well, let's see how much it's moved. It's moved negative I plus 4j in 2 hours. Okay, so velocity is a measure of the rate that the position is changing for each unit of time, so for each 1 hour. So if I want the velocity, I'm going to have to halve this motion. So it's going to move negative a half I plus 2j in 1 hour. Part B asks us for the speed of A. Well, we said the speed is equal to the magnitude of the velocity. So we're going to do the square root of negative a half squared plus 2 squared to calculate that. Let's just calculate that quickly. What was it? Negative a half squared plus 2 squared equals, okay, I'm going to record that as 2.06. 2.06 kilometers per hour. Okay, so the answer to part A is how it is moving. It's moving negative a half kilometer to the west and 2 kilometers north every hour. And obviously the path it's moving along is given by this line. But the speed it's moving is 2.06 kilometers an hour. And if that little sketch I made was drawn correctly to scale, then that would be the length of that line. Okay, write down an expression for the position of A t hours after 1 o'clock as a single vector. All right, so the position we know is the initial position. That's the time where it is at 1300 hours. So that's 3i plus 4j. And we know we have to add on the velocity, which was our answer to part A, times time. It says to write it as a single vector, so I'm going to combine the I components, 3 minus a half ti, and then the j components, 4 plus 2tj. Okay, so that is going to give us its position at any point. If you wanted to check, that things were going on track, you could substitute in time is 2 and make sure you get 2i plus 8j. That would be a good way of checking that you're on the right track. Find the time at which A is directly north of the harbour. So, if it's directly north of the harbour, we want the x component to be 0. So, let's see. Let's do d down here. We want the x component to be 0, so we want 3 minus a half t to be equal to 0. Obviously I don't need the I now, because I'm just interested in the x component. So, 3 equals a half t, so t equals 6 hours. Was it the time or how long? Find the time. So the time was 1300 hours. I need to add on 6. So that is 1900 hours, or 7 o'clock in the evening. Okay, you might want to pause, go back over what we've been looking at so far, and then continue. So we're going to take a little look now at unit vectors and speed and velocity, and just have a little think about how these all relate. So, first of all, we need to define what a unit vector is. A unit vector is a vector that has a length of 1 unit. It's very much in the name there, isn't it? And a unit vector in the same direction as vector B is written as B with this caret symbol on top. And so if we have this vector B, maybe this is B for now, and maybe B is, I don't know, what have I made it? I made it kind of an isosceles triangle. That's a bit silly, isn't it? Let's make it, let's just stick with that. Let's say it's 2 to the right and 2 up. This currently would not have a unit vector of 1. If I wanted to find the magnitude of B, I'd do the square root of 2 squared plus 2 squared. So that is the magnitude of B equals root 8 at the moment. So if I want to make a unit vector in that direction, I want to shrink that down so that it is going in exactly the same direction, but it has magnitude 1. So at the moment, it's got magnitude root 8. I want it to have magnitude 1. I have I've made it root 8 times smaller. I've got to divide by root 8. Or another way of thinking about that is multiplying by 1 over root 8. Okay, so a unit vector that goes in exactly the same direction as B, in this instance, has to be multiplied. It's going to be vector B multiplied by 1 over root B. So I'm dividing by the magnitude. What that does is it shrinks it down and it finds me the vector that goes in the right direction but has a size of 1. Okay, so I'm going to put this in a green box because this is something that we need to learn, I'm afraid. I don't think it's something that's in our formula guide. Let's just have a very quick look. Yeah, we've got magnitudes. We don't have anything about unit vectors. So that's one that we need to learn. Okay, so let's look at using it. And we're actually going to use it kind of in the opposite way to how we've just been talking about it. So we've got a boat that's traveling with a speed of 8 kilometers per hour, but it's traveling in a direction parallel to 3, -4. So 3, -4 is not going to have a velocity of 8. Okay, so that's where our vector is going. What velocity will it have? Well, we need to find the magnitude of that, don't we? Let's give this a name. Let's call it V. So the magnitude of V is square root of, oh, we can see that was 5, can't we? 3 squared plus -4 squared is 5. So at the moment, the vector 3, -4 has a speed of 5 kilometers per hour, but we're actually told the boat's traveling at 8 kilometers per hour. So we need to make it go faster. We need to make the vector bigger than this. So what we've got to do is we've got to take this vector. We don't want to make a unit vector out of it. This has, oops, sorry, don't need a fraction bar in there. This has a magnitude of 5. If I divide it by 5, I'll shrink it down, it will have a magnitude of 1. So that would be a speed of 1. That would be a good way of getting a unit vector, but I actually want it to have a speed of 8. So I'm going to have to multiply it by 8. So there we go. We're going to have to multiply 8/5 by our direction vector, and that will get the actual vector that the boat's traveling along at the correct speed. And of course, we can calculate what all of that is. 8/5 times 3 and 8/5 times -4. So we're going to get 4.8 and -6.4, and that's in kilometers per hour. Okay, so it's taking this idea of a unit vector, but taking it one step further and actually using it to go to a unit vector and then to stretch it up so that it's the correct speed. Okay, I think this is the final thing we're going to try and look at today, which is relative position. So we've got we've got A, which has a position of RA. This hasn't come out very nicely. Let's write it like that. And we have B, which has a position of RB. So these are objects that are moving. The relative position of B from A is the vector from A to B. And we know from what we've done before that to find A to B, we would normally go back down the wrong way. So we'd have to do -RA and then along RB. And that's how we get the vector AB. And that tells us the relative position, which is if you are on, let's say these are ships, because we've been talking about ships. Let's say you're on boat A, it tells you where boat B is relative to your position, rather than relative to a harbour or a port. So it's quite useful if you want to know when you are north of another object. It's also really helpful at finding the distance between two objects at a certain time, or even a maximum distance between them or a minimum distance between them. That's what we're going to look at in this final example.